All right, we need to go ahead and get started. We've got a lot to do today. Let me get over here. I do have your quizzes from last time. I did put the grades in Canvas. All right, so let's get started. Any questions on the homework? Homework?
Number 19?
Oh, I'm expecting a phone call. You know how when you get something delivered to your house, they give you like a window and then they give you a heads up that they're coming? So I'm expecting that call. So if my phone rings, I'm going to take it outside real quick, okay? Okay, which problem?
That's 19.
Number 19? Well, let me take a look. Okay, number 19. Is that what I'm hearing?
That's what I said.
What else? What else?
27.
27 and... That it? Okay, I'll start with 19. 2/3 x to the 2/3. So you're given that f double prime of x is 2/3 x to the 2/3.
Yes, sir.
And you're asked to find f. Right? Little f. But you're given little f double prime, right? So we're going to find little f. So that means we have to go backwards once to find f prime and then backwards again to find f. So our first antiderivative will get us from f double prime to f prime. So I bring the 2/3 down and then I'll have x. I'm going to raise it to a power, but I'm going to add 1 to that. So 2/3 plus 1 is 5/3. And then I put 1 over 5/3 in front, which is the same as 3/5. That's multiplication. So then I cancel the 3's. I have 2/5 x to the, plus c, x to the 5/3 plus c. Right? Okay, so now I'm just going to go again. Right? This is my first derivative, and I don't know what c is. I'm given no information about c, so I'm just going to leave it as c. And so now I go to little f. It's the antiderivative of this. So the antiderivative of this one here, I'm bringing the 2/5 down again. I'm going to leave myself some space in front of it. Here's x. I'm going to add 1 to this again. 5/3 plus 1, 8/3. And then 1 over 8/3 here is the same as 3/8. That's multiplication. Plus, now the antiderivative of c is cx. And then we have another constant of integration, which I'll call d. And then just resolve the number out here. This is what? 1, 4. So what? 3/20. So you have 3/20 x to the 8/3 plus cx plus d. That's it. That's number 19. Number 27. you're given that f prime of x equals 2 cosine t, oh, sorry, it's t. 2 cosine t plus secant squared t. And they give you some restrictions on t, which we really don't need. That's just to make sure that we're within certain bounds so that we don't get something undefined. And then they give you that f of pi over 3 is 4. Right? And you're asked to find little f. So find little f. This time we only have to go backwards once because we're given f prime. So little f of t, we need to bring this constant down because it's attached to the front of cosine. And then we ask ourselves, what is the antiderivative of cosine t, which would be sine t. And then here we ask ourselves, what's the antiderivative of secant squared t, tangent t, and then plus some constant. Now we use this information to actually nail down what c is. So using the fact that f of pi over 3 is 4, that implies to us that when we plug pi over 3 into this expression, 2 sine pi over 3 plus tangent pi over 3 plus some constant, we should get 4 to come out. So we just need to know what these values are. So going to your unit circle, sine of pi over 3 is what? Sine root 3 over 2. It's the y coordinate on your unit circle. You're at pi over 3, which is up here. Sine is the y coordinate. Right? Remember, this is 1/2 root 3 over 2. So sine of pi over 3 is root 3 over 2. Are y'all okay with that? Yes? And then plus, yeah, the 2's will cancel. Tangent of pi over 3 is the y coordinate divided by the x coordinate. So root 3 over 2 divided by 1/2. 2's go away, you just get root 3. And then when we have plus c equals 4. So cancel these 2's. And now what you have is, what, root 3 plus root 3 is 2 root 3's plus c must be 4. And solving for c, you get c must be 4 minus 2 root 3, whatever that number is. But this is our constant now, so we can actually come back into this function right here, where we have found little f, replace c with this number, and we have f. So the final answer is this line with 4, ooh, it's dead. Uh-oh. Thought I had another color here. let me try this one here. They're all over the room. It's just a question of do they work. 4 minus 2 root 3. And then box that up, that's your answer.
What number was that?
That was number 27. Okay, let's get moving. If you have any other questions, let me know. But not right now. Sorry. How are y'all doing today? Y'all okay? Feels, yeah, I'm dragging right now. I don't know. This whole thing where my Tuesdays and Thursdays, I'm getting into my office like around 8:45, and I don't have anything until this class, and I'm just like, oh. You know, I'm watching YouTube videos and on math-related stuff, of course, but, you know, it's just still, man, it's a drag. I need to give more quizzes or something, that way I have something to grade. Okay, we're going to move to 5.5. all right? We're going to probably knock this out, hopefully pretty quick, so that we can get into the next section, which will be, we're going to skip from there, I believe, to 6.1. Is that right? Yeah. So let's see how we do with this. So 5.5 in the notes, substitution rule. So first, some notation. You know, we were saying before, you know, that we had this little f, and then we had this concept of finding its antiderivative, right? I'm just going to put anti, right? And we called it capital F. And so every time I wanted to tell you find the antiderivative, I would have to tell you find the antiderivative, right? But we have a different notation that we use that actually tells you find the antiderivative, and it's what's called the integral. So if we're given a function little f of x, if we wish to find the general antiderivative, then we write the following. So it's this symbol, okay? And then we write the function here, and then we tack on to the end of it, and it's like multiplication, this thing dx. All right, so let me go through what each of these things are. First of all, the entire thing, all right, is called the indefinite integral. Right, the whole thing together is called the indefinite integral. This symbol here is called the integral sign, and it's actually an elongated S because it actually is a summation, which we'll talk about, but it'll be much later. Like after we get through most of chapter 6, we'll actually figure out why it's a sum. And then f of x, which is the function we're trying to find the antiderivative of, is called the integrand. It's kind of related to, you know, if you had a radical, the thing underneath it was called the radicand. Here, when you're doing an antiderivative, there's an integral sign. It's called the integrand. The dx is called the differential. And the way I want you to look at it right now is that this just keeps track of what the independent variable is in the problem. So if this says dx here, that means that your integrand is, you're treating the x's like the variables, all right? We're not going to see anything other than that, but if you go on and do more calculus, you'll have functions in here that are functions of more than one variable. So this right here keeps track of what you're treating as the variable, all right? Okay, and then when you actually figure this out, you find the antiderivative, right? And we call that capital F of x. So that's called the antiderivative, right? And then the c that we add on the end is called the constant of integration. So this whole process of finding antiderivatives, okay, the whole process of finding antiderivatives is called integration. So in Cal 1, we did the process of finding derivatives. We called it differentiation. And now in Cal 2, when we're going backwards, we call it integration. And that again ties into the idea of this being called integral calculus. Cal 1 is differential calculus. This is integral calculus. All right, so some things we've already seen. We saw the power rule last class. You used that on your homework. And we said that this power rule takes care of all powers of x. And there was that one special case where n was -1 where it became the natural log. But that formula we should have. In addition to that, on your formula sheets, on page 6, reference page 6, is a list of 29 integrals. And so all of these use the notation that we are learning here today. So for example, I'm going to just look at one of these here. Formula number, let's say formula number 7 says this. It says that that's equal to what? Sine u plus c. So the integrand, the function we're trying to integrate, find the antiderivative of, is cosine of u. So we're using u instead of x, all right? And the differential tells us, yes, u is the variable, right? So the antiderivative of cosine is sine plus some constant, right? Now this table gives you a bunch of formulas, and you need to become familiar with at least the first 20, all right? You should be, I'm not saying you need to memorize them. I'm just saying that you need to know that they're here for example, if you have something like this, integral of 1 over 4 minus x squared dx. Okay, and when you see that, you're like, well, I'm not quite sure how I'm going to do this, but wait a minute, hold on. Looks like formula, which one? Look at 19. 19 says du over a squared minus u squared, right? That's it. So that formula is the same as this. The du is like multiplication. It can be slid out to the side like that. And then the a here in the problem, what do we say the variable is here? U, because the differential tells us that. So we're going to treat the a as a constant. So for our formula over here, what we're trying to do, using 19, we can see that a for us would be what? 2, right? 4 is 2 squared. So that right there falls into this formula pretty nice, doesn't it? And so what is the answer? We don't have to do any work. What is the answer? 1 over 2 times a. Now remember here, that's a squared is 4, so a must be 2, right? So 2 times 2, that's our a, and then natural log of the absolute value of u. What's u for us? U is actually x. Then plus 2, then x minus 2, and then close it, and then plus some constant. All right? So it'd be 1/4 the natural log x plus 2 over x minus 2. That's it. We'd box it, we'd be done. So please be aware that there are a lot of things on here you've seen, like mostly 1 through 10 are all probably things you've pretty much seen. But the ones on the right, 11 through 20, some of those aren't as obvious, or things that you didn't get in calculus 1. So just be aware of that. Now, if you have a book, these formulas, if nobody tore out your formula sheets, if your book still has formula sheets in it, I stopped at the second page 6 of the formulas, but there's actually page 7, page 8, page 9, page 10. There's actually 120 formulas in this book for finding antiderivatives. And I've seen books as thick as this book full of formulas for antiderivatives. I mean, there's a bunch out there, right? A lot of times when you get to like a physics class or something like that, there's integrals that come up all the time. And so instead of having to figure out how to find the antiderivative, they usually have a formula for it already, so you don't have to do it. Just sharing that with you. But we're going to try and do a bunch of integration without needing the 120 that are in the book. We're going to do a lot of it just by different procedures. Okay, any questions? No? All right, next thing. Substitution. All right, so let's talk a little bit about substitution. Right now, the only way we can find an antiderivative, right? The only technique we really have is that we have to hope it's a power of x, right? Or we have to hope it's something we saw in Cal 1, like secant squared. The antiderivative we knew was tangent, right? Tangent derivative is secant squared. So that's all we've got right now. This rule, substitution rule, is really our first kind of technique, our first tool in our toolbox of trying to find antiderivatives. And it's the most basic one, but you can't do anything past this if you don't get this rule down. Okay, so everything builds off of something like this. So we'll start with, let's just take a look at Cal 1 problem, which would be finding the derivative of that. So if we find the derivative of this, let's see who's awake today. I'm going to call on Paul. But I know you're writing things down, Paul. I'm just trying to wake myself up, so I just figured we'd talk. Okay, so cosine of what? X squared times 2x. Okay, that's it. So chain rule, right? And of course you could reorder it. Sometimes we like to put those numbers in the variable out front, and we're done. That's it. That's Cal 1. Now, think about this the other way around. Okay, so let's say we start there. And I'm actually, see in my example there, I want us to look at, forget the 2's there. Let's just look at this problem. Right there. Okay, so forget the 2. The 2's not there. I mean, it's here, right? But this is a separate problem. So the issue we have here is that there's multiplication here, right? There's our multiplication. And we talked last class that antiderivatives, when you have products, is not easy, right? It's not simple. You can't just find the antiderivative of each one. So how are we going to go backwards from this to this, right? I mean, how are you going to do it? Are you just going to look at it and go, sure, that's the derivative of 1/2 sine x squared. Because, oh yeah, that 2's not there, and I know that the 2 would come out in chain rule. Are you going to be able to see that far ahead? You understand what I'm saying? That can be somewhat challenging, right? So there's got to be some process that allows us to go backwards with more efficiency. And that's what substitution rule is. So let me show you what the strategy is. I have it in 6 steps. What we're going to do is we're going to look at the integrand. The integrand is the entire thing here, right? I'm going to look in there and I'm going to try and find something, okay? Something in here. And also within here, the derivative of that something is sitting in here. And then on part 4 it says the derivative that you see might be off by a constant, and that's okay. All right, so what do I mean by that? I mean, look around in here. Oh, that's the call. Let me turn this off real quick. Y'all look. Okay, let me make sure. Did y'all get it? I thought someone was going to come up here and write it down. Okay, so we're looking for something and its derivative. We're okay to be off by a constant, right? That's where we are. So you see x squared? What is the derivative of x squared? 2x. You see an x? So that's the something, and that's its derivative. We're off by 2, right? So what we're going to do now is we let the u be something. So this is where we're going to make a substitution in the problem. I'm just going to walk here on the side. I'm going to say, look, let u be x squared, right? That means everywhere I see an x squared, I replace it with a u. Now, the next step is to take the derivative on both sides of this equation implicitly with respect to x. So what's the derivative of u with respect to x? du dx. And then what's the derivative of x squared? 2x. Right? And then derivative of x with respect to x would be 1. So this is it, right? Everyone with me? Okay, now the next thing I'm going to do, and this is going to be pretty much standard the way I'll do it the rest of the semester, is I'm always going to clear this dx on this side, basically multiplying both sides by dx. So getting du is equal to 2x dx, right? And remember, that's multiplication right there. So I look over here, and I said I saw something in its derivative. I'm just going to rearrange it a little bit so that perhaps it looks a little easier to work with. I won't always rearrange it as we move on. I'm going to put the cosine x squared here. I'm going to slide the x that's back there right here and just push it right in between those. X dx. Remember, that's multiplied, right? So I have an x dx in the problem, right? I have x dx here. And over here, I have an equation that actually has x dx in it also, right here. The thing I don't have is the 2, right? So I don't want this 2 here. So what I'm going to do on this equation is I'm going to multiply both sides by 1/2 or divide both sides by 2, however you want to look at it. I like to put it as a number out in front. So 1/2 du equals x dx. And so once I've got this matching up exactly with what's up here, what I'm going to do is actually make the substitution now. I'm going to rewrite the integral, and everywhere I see a u, I will replace it with x squared. Everywhere I see an x dx, I will replace it with 1/2 du. So let's do it. Now I'm using an arrow here to let you know that I am rewriting the integral, but my variable has changed, so I'm not quite saying they're equal. I'm just saying this is being transformed into some new integral. Here's what it is. What? Cosine of u, so cosine u, times, and then the x dx we said was 1/2 du. And at this point, I can take that 1/2 and I can actually slide the 1/2 in front of the cosine and then actually out in front here, because remember, with antiderivatives, the constant, if they're attached to a function, it's just going to come with us. So I'm just going to put here, this one equals 1/2 times, so there is multiplication there, cosine u du. That's all we'd have left. And this, because we've changed the problem, the variable in the problem, we actually know what the antiderivative of cosine u is, right? It's sine u. So this becomes no more integral sign, right? Watch. No more integral sign, 1/2's coming for the ride. The answer is sine u, right, plus a c. So when you actually find the antiderivative, two things happened here. The integral sign went away, right? And the du just kind of disappears. And that's because the du is only keeping track of the variable. Yes? Question? No? No? So some people like to say, like, the integral sign goes away and the du somehow becomes the constant or something. So you don't sit there and go, where'd it go? It's the constant. That's not really what it is, but let's just, if that helps you, remember the constant. All right, so this is our answer, but we're not done because our original problem was in terms of what variable? X, right? So I need this to go back to x. But I know what u is. U is x squared. So now in the last line, and this will be my final answer, is that this equals 1/2 sine u, but u is x squared plus c. And that's it. And we could check that ourselves to see that that's correct by doing what? Taking the derivative, right? So if we took the derivative of this, you would get back this. All right, so the key is to look for something, right? You're trying to find something in its derivative and then make a substitution and hope for the best, right? That's what it says. Make the substitution and go for it. See what happens. And that's it. That's substitution rule. Have a good day. We should probably do some examples, right? Okay, let's try some. All right. Find the antiderivative of x squared square root x cubed plus 30 dx. Use the substitution u is equal to x cubed plus 30. So in this problem, I'm actually going to lead you to the answer. I'm going to tell you what the substitution should be. All right, so I'm telling you what your u should be here, but let's see why that is the choice of u. You have this integral, right? Could you use the power rule from last class? Is that even possible here? Because there's multiplication, you can't just do this and this, right? You can't split this into two because there's some in there. So there's no way you could use any of the rules from last class. It's definitely not the derivative of something you learned in Cal 1 that was like a simple formula, like cosine, right? So this is something that's going to require a little bit more. So now we go to this technique. We look for something and its derivative, and we hope that we're off by a constant at most. So we look underneath the radical, and we see we have a cubic function, right? A cubic expression. And we know that the derivative of a cubic expression would be quadratic. In fact, the derivative of x cubed plus 30 is what? 3x squared. So I have an x squared. I'm off by 3. That's okay. I at least have the x squared, don't I? Now, why not choose for u instead of this? Why not use this? Why not take the whole thing with the root? What would the derivative of this be? It'd be 1 over 2 roots of x squared plus 30 times 2x, right? And the 2's would cancel. Now, what we said for substitution is that you want to see something and its derivative. So if I chose this, do you see that there? Yes, there it is. Do you see its derivative there? Do you see a square root of all this junk in the denominator up there? No, right? So this would actually be too much. You actually picked too much of a u for this to work out. Does that make sense? So you're trying to find this balance, picking enough to make it work, not too much and not too little. What would be too little? This is a good one here. How about if I just say u is x? Because look, what's the derivative of x? 1. Do you see a 1 there? Of course there's a 1 there, right? But if you actually make this substitution, what will happen is every x gets replaced with a u, and the dx gets replaced with du. And what you have is the whole problem rewritten exactly the same with u's instead of x's. So this would be not quite enough of a u to choose. This would be too much, and that's perfect. Yes?
Why did you just pick x cubed?
X cubed. Oh, why didn't y'all tell me this should have been cubed? Why didn't y'all tell me that? Cubed, right? Cubed, and this would have been 3x squared. That wouldn't have canceled. I'm sorry. Right? Okay, I should have caught that earlier. In any event, this didn't work anyway. right? So what about just x cubed, right? That would actually work too, okay? But what'll happen, see, I don't want to foresee this too much, but I'll try. If you pick this to be your u, right? Then in your new integral, this x squared in dx should be part of your du. It should be out here somewhere. But you're still going to have the square root of what? U plus 30, right? Do you know the antiderivative of the square root of u plus 30? Not right off the hand. But if the whole thing gets replaced with u, then it's just the square root of u, and the antiderivative square root of u we can use the power rule on. So you might have to learn that lesson by doing some and seeing that it takes you a little longer if you don't pick quite enough. All right, so let's use this substitution, right? Here we go. So what is du? What is the derivative there? So du dx is 3x squared, right? And then that means that du is 3x squared dx. Do you have a 3x squared dx over there? Not quite, right? You have square root x cubed plus 30 times x squared dx, right? You have the x squared dx. So let's go ahead and try and isolate this x squared dx here on this equation. So do what? Multiply both sides by 1/3. And so what I'll do is I will replace this x squared dx with 1/3 du, and I'll replace the x cubed plus 30 with u. Are there any questions? You'll see this happening? All right, so let's see here. Yo. That's your name, right? Did someone mess with you? Or did you put that? You put that?
I put yo, whatever.
Okay. All right, yo. All right, yo.
Yo.
So, yo. Oops, I'm trying to silence this now. What is that integral going to turn into? Yo. What am I replacing x cubed plus 30 with?
You're gonna replace it with the you?
Yes. What is x squared dx being replaced with?
So you're gonna replace it with the
1/3 du, right? 1/3 du. Does anybody have questions on that? Okay, so now what I'll do is I will clean it up. I'm going to take that 1/3 out to the front. And the square root of u, Chris, is going to, should I leave it as square root of u if I'm going to take the antiderivative? What should I write it as?
X squared plus 30.
Not yet. We haven't done the antiderivative yet. But if I want the antiderivative of the square root of this, do the 1/2, right? So change it to u to the 1/2 first, and then du. And now this is a power rule, right? Your variable's u now. It's a power rule, so I have the 1/3 out front, and then I'm actually taking the antiderivative now, so the integral sign is going to go away. I'm going to write u, and let's see, Kelly. I couldn't see your name tag there. I know you were trying to look over the camera there, so I'm calling on you to get you going here. Antiderivative u to the 1/2. U to the 3/2, 2/3 in front. And
plus c.
there you go. So remember the du afterwards, you can look at it as becoming the plus c, so you don't forget about it. Because everyone always asks, what happened to the du? It's just keeping track of the variable, but if you want it to do something, then let it be your c or something. All right, so this becomes, let's see, 2/9 u to the 3 halves, right? Plus c, and then we can actually go back now and replace u with what u was. So what was u? X cubed plus 30. The entire quantity, though, raised to the 3 halves plus c. And that's our answer. And we could always check it by taking the derivative, couldn't we? I have this vivid memory from my childhood when I was about 9 years old. My grandfather had a V8 engine up on an engine stand in his shop, and he had it all hooked up, and he had it running, and it was really loud, and I had little earphones on, and he had me holding a camcorder, like the old ones with the VH tapes that would go in them, and he had me holding it while he was demonstrating. He had come up with variable valve timing for an engine, and he was doing it years before it came out. And he was just doing it and showing me, and I didn't have any idea what it was, but I was recording. So after that, you know, I'm in there, and it's like, you know, it smells like exhaust in there, and he's doing something on paper, and he's asking me, like, okay, I have three fifths, and I need to subtract from that like 1/7, and he's doing some arithmetic like that, fraction stuff. And I had no idea how to do it. I was so terrified. Like, I sucked really bad at fractions for a long, long, long time. You know, so I just remember just feeling terrified that this old man could do all this fraction stuff in his head, but I couldn't do it at all. Like, I couldn't do it. And it took me, you know, till about calculus to really get good at it. So I guess when I'm calling on you, I'm expecting you to add 1 to 1/2. I know for some of you might be sitting there going, I hope he doesn't call on me and ask me to add 1 to 5/7, you know, but you want to get comfortable with that because you don't want that slowing you down, all right? Get good with those fractions, get quick with them. All right, shall we do another? Yeah, of course. Of course we should. All right, this one, I'm not going to tell you what the substitution should be. Hold on. This one's tricky. So, I don't think this falls into the category of just basic power rule, right? This is not the derivative of something you know from Cal 1, because there's a lot going on in here, right? So you're looking for something in its derivative. Let me make sure I think I wrote that down wrong. Yes, that's a 4 down here, sorry. I was like, uh-oh, that's not going to be good. All right, any volunteers for a candidate for u? X to the 4th? Because you see its derivative? What's its derivative? 4x to the 3rd. Do you see x to the 3rd? Okay. That's why I put this problem up here, because that's not correct. That's not going to work. Now, let's pay attention to why. You do have x to the 4th, but you actually have 1 over x to the 4th. You don't have, I mean, there is an x to the 4th down here, but if you slid this out here, it's actually 1 over x to the 4th, yes? And more importantly, the derivative of x to the 4th is trapped inside of a function. There are two things that you really don't want to have happen when you pick your u. You don't want the derivative of that u to be trapped by anything. You don't want it to be stuck inside of the argument of a function. You don't want for it to be in a denominator. You don't want it to be under a square root. You want that derivative to be by itself, just a factor that you can factor out. Because remember, don't we get that du and put it over here and try and get it to go away and match it up with something? right? If it's stuck in here, how are you going to pull it out? And you won't be able to. So maybe something else. Yes? 1 over x to the third. That doesn't seem as natural, but that's the same as x to the negative 3, right? And the derivative of this is what? Negative 3 x to the negative 4, right? Which is the same as negative 3 times 1 over x to the 4th, isn't it? Do y'all see that? And didn't I just say x to the 4th? That is actually a 1 over x to the 4th. Zach, do you see that? Yeah? Okay. That looks like it's going to work. So let me just finish writing this one line. I have du is equal to negative 3 times 1 over x to the 4th dx. So all I did there is what I'm going to do every time, which is bring the dx over here. And so what I'm going to try and do is see if I can manipulate that expression up there to make it look something like this so I can do my replacement. So I'll rewrite the problem over here as secant squared times 1 over x cubed times 1 over x to the 4th dx. So all I'm doing is sliding that secant squared out here and leaving a 1 over x to the 4th and then the dx. Because it's all multiplication, it doesn't matter how I put those together. This right here is what I'm trying to get to match up. I have it right here. So again, I'm off by a constant, negative 3 is what I'm off by. So I'm going to divide both sides by negative 3 or multiply both sides by negative 1/3. I don't think I want to erase that. I'll write it down here. So this will be negative 1/3 du equals 1 over x to the 4th dx. And Ruben, how should I rewrite this, Ruben? Since I've got it all, I think I've got it all ready to go for you here. Okay, so integral sign, then what? Secant squared u times negative 1/3 du. That it? That's it. So we replace the 1 over x cubed with u. We replace the 1 over x to the 4th dx with negative 1/3 du. That's it. We can pull the negative 1/3 out of that completely and then hope that we know the antiderivative of secant squared of u. And you do, right? It's tangent u. So this becomes negative 1/3. You want me to go ahead and do it now? Or do you want me to rewrite the integral? You want antiderivative now? Yeah? Tangent u plus c. And then replace u with what it was. What was u? 1 over x cubed plus c. We're done. So we're starting to pick up a method that is having some success with some of these more complicated looking expressions, right? We have not checked any of these, have we? I mean, like we haven't checked any of the answers, but we could just take the derivatives. Okay, let's try another one. How about what the hell? I'm so sorry, everyone. I'm just going to make sure this is not them. Hello? Yes? It's a 9, actually. There you go. Is that better? It's a Q.
That's a key.
So while you're trying to figure out what U is here, the thing that's going to get really difficult with this is that, you know, we have the substitution is the first kind of approach to doing things. After we do this, we're going to do integration by parts. That'll be the next sort of technique. Then after that, we're going to have what are called trig integrals. Then we're going to have something called trigonometric substitution. And then we're going to have partial fraction decomposition. And so we're going to have this like big old toolbox full of things that we can use to try and find antiderivatives. And so when you're faced with a problem like on a test or like in another class, nobody's telling you this is done by substitution. That's the challenge, is for you to be so good at all the methods that you can just see what method you're going to need to use. And that takes a lot of practice to be able to see it ahead of time. All right? So we have to kind of keep ourselves grounded here. Even if you kind of get this, you have to understand that when everything starts to get piled onto this, all the other techniques, you almost forget about this technique, you know? And so you try something really hard when it was something very easy. Or maybe you make a problem that's really hard too easy. And I don't know if that makes sense. Okay. Anybody have a U for me? E to the x? So you see, where are you seeing an e to the x? I see two of them. I see an e to the x and an e to the 2x, right? So you're saying, which one are you treating as the u? Both or this one? Okay, if you treat this as e to the x, I'm going to write it down. U is e to the x. What is its derivative? Its derivative is e to the x dx. Now, this was really du dx, and I brought the x over. I'm going to stop doing du dx and just bring the dx over every time. All right, so if u is e to the x, its derivative is e to the x dx. I want to know where you saw its derivative then. I'm just going off. You said that you were treating this as the u? Because if that's u, then where's its derivative? It would be down in the denominator, wouldn't it? And I said we don't want the du, the derivative of it, to ever be in a denominator or under a root. We want it all by itself, don't we? That's what I said. So, I don't know. Should we stick with it? What do y'all think? Anyone want to keep this? Anyone want to try something different?
For you, I guess in parentheses 9 plus e to the 2x.
You want to try the whole thing?
To
The whole thing?
yeah.
So okay, so this is our second candidate for you. I'm not going to tell y'all which one's going to work yet. I'm just trying to get your train of thought here. E to the 2x. Okay, let's look at its derivative. Derivative of 9 is 0. What's derivative of e to the 2x? E to the 2x times 2 because of chain rule, right? Okay, so if that whole thing is u, do you see its derivative anywhere? I see e to the x dx. That can be slid out, can it? But I don't have e to the x dx. I have e to the 2x dx. Sean?
Can it be a 3 plus ex? U?
3 plus, you mean like 3 squared plus? I'm not sure what you mean by 3. Because of the 9?
Yeah, change that to 3 plus e, and that's squared.
Ah, okay, I see what you're saying.
Squared.
Like change it to 3 plus e and then squared, like this? I think that's what you're saying. But this is not this, because you would actually have to FOIL this out and you'd have,
Right?
oh yeah, e to the x, like this? Is that what you meant? I don't know, yes? Or did you want the x out here? Either way, if you squared this, it won't be this, because you'll have some middle terms. What's that? What do you got, Luke?
I was going to say 1 over what I said there. Yeah, 1 over 9 plus.
You want to go 1 over the whole thing as u? The derivative of that might be pretty ugly, though, right? If you let u be 1 over the whole thing, the derivative would require like some quotient rule and stuff to get that. You can't split it into two fractions, right? Because you have one numerator, two denominators. What's that?
Make u equal 2x.
If u is 2x, the derivative of 2x would be 2, and you're off by a constant, but that would almost be the same as doing x, just u is x. Okay, so look, the correct way is this way, but the problem is that this is not the u, this is the u, and you have to rewrite it first. So watch. Isn't that the same thing? Isn't e to the 2x e to the x squared? Isn't it? Because you just multiply these two together, 2 times x is 2x. Now, if this is your u, right? If this is your u, the derivative of e to the x would be what? E to the x dx, which you have right here. So that might work. Maybe what I can do is, I'm going to come down with this a little bit. I'm going to rewrite this as integral 1 over 9 plus e to the x squared times e to the x dx. So I'm sliding that e to the x to the outside so that you can really see it sitting there. So what I'm going to be able to do is replace this right here with what? That's exactly what I have here, right? That will be replaced with du. I'm going to be able to replace the e to the x right here with what? U. And then let me just see what I have. All right? I'll look at it after that. See, that one was a little more hidden, wasn't it? Okay. So this becomes a new integral. I have this right here, 1 over 9 plus u squared. 1 over 9 plus u squared times e to the x dx is du. That looks a whole lot like what? There was one that I told you to remember, arctangent, right? The arctangent one, except the arctangent, didn't it have a 1 here? Yes? Not a 9? So please refer to your formula sheet now, because if you look at the formula number 17, it's a more generalized formula for arctan. Formula number 17 says that if you have an integral 1 over a squared plus u squared du, do they put u squared in front of a squared? It doesn't matter, it's addition, it can be either way, right? That the antiderivative of that would be what? 1 over a arctangent of u over a plus c. Now, what the formula I gave you, what was the number I had here in the formula I gave you when I first introduced you to it? It was 1, wasn't it? And that means that a would be 1. And that means this is 1 over 1, which is just 1. And this would be u over 1, which is just u. So that's why if this is a 1, it's just arctangent of the variable. But this is more general. If you have another number here, you can actually deal with it. Well, no, it doesn't even have to be a perfect square. So like if your number, if this right here, we're going a little off topic, but if I had this, I could still do that because a would just be the square root of 5. Right? Because what number squared gives you 5? Square root of 5 gives you 5 when you square it. So this does not have to be a perfect square. A lot of times it is because they like to keep the numbers clean, but by no means is that necessary condition. Right? Yes? Okay. All right, so according to this formula, this will be equal to what? 1/3, because a is 3. Arctangent of u over 3 plus c and then replace u with e to the x. And we're done. I think it's time for you to try one. You can do it.
Would it matter if we use positive 3 or negative 3?
Where?
For the square root of 9?
That's a good question. No, it'll be, does the formula have absolute value or no? It doesn't. No, it'll be the principal root, so it'll be the positive one. You have to use the principal root. All right, so how about I'm going to give you 2 to work on, all right? One of them will be kind of easy. The other one will be a little bit harder, all right? So let's see how you do. Y'all can work together if you'd like. First one, integral 5 plus 2x to the 7th over square root 40x plus 2x to the 8th dx. The next one, so we'll call this problem A. Problem B is integral sine 2x over 4 plus cosine squared x dx. I'm going to give you about 10 minutes to see how far y'all can get with those 2 problems. All right? You're free to help each other out, work with each other.
Can I divide that by n?
Absolutely. That's exactly what you want.
40x plus 2x.
What you got? Did you divide by 8? Yeah. Okay. So you wondering what to do with this?
I was just stuck. I haven't
Okay.
kept going yet.
Yep. Just remember your integral sign. Keep track of everything. Back here? How about on the first one?
Yeah, that's what I'm doing.
Okay, so do you see something? Okay.
Second cloud. Choose this.
Yeah, because the derivative, that's a 7th degree. You have 40 plus, so you take the derivative. Go ahead, you scratch it out, but write it down again. Write down that derivative again.
So I take the derivative of this.
Uh-huh.
Plus 40.
Uh-huh. And then put dx behind it. Throw it in parentheses because it's two term. No, the 16.
Gotcha. 'cause
Yeah,
it's-
and then make that equal du. So du in front of that. Okay, so that's what you have.
Yeah.
So you look up, and what you have up top needs to somewhat match that over there.
Okay. So I just have to make it look like this.
Yeah, can you? Is there a way you can do it? What is the number you need in front of the x to the 7? For it to match, you need it to be a what? Like you have 16, what do you need it to be?
I need it to be 2.
A 2.
Plus 8.
So you'd have to pull an 8 out of there. Can you pull it out of both?
Yeah, okay.
Okay, so just factor an 8 out of both sides. So put du equals, pull an 8 out.
Okay. I have what?
Yep, dx. Now, do you see that 2x to the 7 plus 5 dx
So it'd be
matches
1/8.
1/8? There you go.
Awesome. Thank you.
You got it?
Yes, sir.
Okay. So you pull an 8 back there. Yes. So that was u. This one is u to the negative 1/2. There should be a constant. You lost a constant somewhere in there. I think you were good up to this point.
Yeah,
Right.
that's the 2.
So, right, this was the 1 over square root. So when you add 1 to that, then you do the little thing in front, flipping. You're gonna pick up a number there. Yeah, that's the only issue I saw there. How are we doing here at this table? Anybody have any? Getting the first one?
Yeah.
Yes. How about you? Okay. So you got your derivative. When you took your derivative here, you put a 40x, yeah. So when you took the derivative, I think that might be the issue. When you take derivative of 40x, you get 40.
Oh, that's what.
Right? And then at this point, yeah, just, and then 16. There you go, the 1/8. You see how the 1/8 will make it look exactly the way you need it? Yeah. All right, so you got, did you get the first one?
I think I'm getting
Yeah, now you divide by 8. Okay. Yes, you're on your way. How we doing? Did you try something for the first?
I did. I put a u for the 40x.
Plus 2. The derivative of that was 40 plus 16x squared.
I'm having trouble factoring that out.
Okay, so you have this, right? You have 40 plus 16x squared dx, right? That's what you have. And what you want it to be, it would be really nice if it was a 5 plus 2x to the 7. Sorry, to the 7. That's what you have, right? Is your du? Let me just double check it, right? That's what you got. So you would really like this to match up with the 5 plus 2 to the x to the 7. So notice that these both have an 8 that you can factor out. So if I pull an 8 out, 8 times 5 is 40. 8 times 2 is 16. Do you see that? And then this matches what's up there on the top, so you just divide by 8 on both sides. So it's a little bit hidden in there. You have to be careful with it. Yep. So it was, be careful here, that's u to the negative 1/2. Because it was on the bottom, right? So when you bring it up, it's negative 1/2. All right. I'm about to run through these, okay?
Sorry, I'm still on A, but I got to here.
Oh, yeah, I know. And then we have to find
Does that look correct? Am I going the right direction?
This is okay, but not sure what you, okay, this is okay, this is okay. Not sure what you're doing here.
I think I was trying to plug it in.
You have to find the antiderivative of this right here.
Okay,
Yeah,
sorry.
that's the same as u to the negative 1/2. All right, I'm going to run through these, all right? Let's do this first one. I think most of you chose the u to be the 40x plus 2x to the 8th. And then when you take the derivative of that, you get 40 plus 16x to the 7th dx. And you're trying to see if this somehow can appear up here somewhere. And it took a while for some of you, but I think now most of you are on the same page, that if you factor out an 8 or divide this side by 8, then you get that exactly. And so that means you'll wind up putting a 1/8 on this side, and then this will become exactly the 5 plus 2x to the 7th dx. And then you have to rewrite the integral. And I saw some of you getting a little hung up on this part. When you rewrite this integral, this entire piece right here is going to become what? 1/8 du. So I'll pull the 1/8 out and I'll slap the du on the back. And then what's left is this square root of u, but it's on the bottom. So 1 over root u is the same as u to what power? Negative 1/2, right? That's the same as 1 over the square root of u. Then you have to use the power rule on that to get the antiderivative. So the antiderivative is 1/8, and then u, going to add 1 to this power, so that gives me positive 1/2, and I put 1 over 1/2 here, which is the same as 2 plus c. And then that's 1/4, right? And then what's u? All that stuff, right? 40x plus 2x to the 8th, but all of this to what power? 1/2, or square root. You could write square root, that's fine, plus c. And that's your answer. So just be careful on that. That's a negative 1/2 here, not a positive 1/2. The next one, I'm not sure if anyone got to this one or not. You did? Okay, so you had what? Sine 2x over 4 plus cosine squared x dx. So you got it? What did you use for u?
4 plus cosine squared.
The whole denominator?
Yep.
Okay, so u is equal to 4 plus cosine squared x. Then the derivative of 4 is 0. This we have to use chain rule. So 2 comes out, cosine x, times the derivative of cosine, which is negative sine, so I'll put the negative out front, sine x, and then we slap that dx on the end. Now Ron is telling me that he did this because, and he said it worked. I haven't asked Ron why he did it, but Ron, I don't see the derivative sitting up there, but apparently you do.
Sine 2x is equal to 2 sine x times cosine.
That's right. So you had to know that double angle formula from pre-cal.
Yep.
Yes,
I remember
you remembered it
with
with a little help of the formula sheet. But at least you kind of remembered that something with that, right? So a very important formula from pre-cal was this one. Sine 2x is equal to 2 sine x cosine x, the double angle formula for sine. So anytime you see sine 2x, it can always turn into this. And look at, that's this right here, right? This piece right here. And that's exactly what we have here, but we're off by what? A negative. So I just divide both sides by -1 or multiply both sides by -1. So negative du is equal to 2 cosine x sine x dx. I hope everyone sees what I'm saying. This right here, forget it's there and just put that there instead. And then they match up. So if that's the case, then when I rewrite this integral, the 2 sine x cosine x dx, that whole thing is going to be replaced with what? Negative du. So I'll do it this way. Here's the negative. It's like a -1. The du I'm going to put out here in the back. And then I still have the 4 plus cosine squared x, which is the u, right? But it's on the bottom. So 1 over it. And now we better know how to do that, right? If we're going to be able to do it. I mean, go anywhere. This is natural log. So this is negative, because the negative out front. Natural log of absolute value of
Cosine squared x.
u, which, yeah, I'll do that next step. That's this, right? Then we will replace the u with what u is in the problem. So this is equal to negative natural log of, what is it? What was our u? 4 plus cosine squared x plus c. And that's it. Now I'm going to show you something the book, like if this were a problem in a book, they might have this as the answer. And my question to you would be, what did they do? What did they do?
Let's add -1.
How does this become this? So you have to go back to this property. Remember this property. Natural log of x to the n is equal to n times the natural log of x. The property of logs from college algebra says that if you have x to a power inside of a log, the power can come out front and become a number in front. It works the other way around. If you have a number out in front of a log, you can move it up as a power. So what we basically did is we took this negative, or they took the negative here as a -1. They moved it up as a power right here, -1. And when you have something to the -1, it basically drops it down. So that you took this whole thing and dropped it down, and it became 1 over it. So the negative goes away in front, and it creates this fraction. Just be aware of that, because books, answers in the back of books, they love to do things like that, and you're like, what the heck? Okay. So look, your only hope in getting good at this is to keep trying problems and doing as many as you can. So the homework for this section, did I give you homework? Let me see what it says here. Oh, no, there's no homework? I didn't write it down anywhere, did I? Okay, so I'll tell you what to do. So this is off of page 252. And you should do 15 through, oh wait, no, this is not the right page. That's the last section, hold on. It's like, what? Section 5.5. I'll give you the same homework assignment as last time. All right, so you should do page 306. 1 through 36. Yes, all. All. So what I suggest you do is start with the odds, knock out the odds so you can check your answer in the back of the book. And then start working through the evens. All right? That's a lot of work right there. But I guarantee you that if you put an honest effort into this, and when you get stuck, you go get help, or you go to the tutoring lab, meet up with a group of people, y'all work on them together, whatever. If you work through these problems, you'll be at least in the game still. If you are struggling with these two quiz problems, these two problems I gave you just now, if you're struggling with those, then if you do no homework, this is going to be an impossible task. You have to practice. All right? So please, come reach out to me, get help. But we're moving on. I don't have a lot of time, but I want to introduce the next topic. Now, I'm not trying to rush you, okay? Don't get the impression I'm trying to rush through this. I told you earlier, another class in the past, a past class, what did I tell you? I was trying to kind of move quickly. The harder stuff's still to come, and I don't want to be trying to rush through that. So for most of you who have taken Cal 1, a lot of you had seen this. Let's do a show of hands. How many of you had seen substitution before? Show of hands, okay? How many of you have seen integration by parts? So a few, like 2, I see 2. So integration by parts, this is going to be brand new for most of you. All right, so this is a new formula, a new approach. It's different than substitution, extremely powerful, but you got to know when to pull this tool out. You don't do it for everything, all right? So the way I'm going to introduce this, I'm going to talk through what this is saying here in a second, but I think I'm just going to write it down on the board. Do you remember from Cal 1 that if I had, let's say, 2 functions, I'm going to call one of them v, I'm going to call one of them u. So these are 2 functions. This is a function of x times another function of x. But instead of calling it f of x and g of x, I'm going to call it v and u. Is that all right? Yes? Okay. I could also have written it this way, u and v, right? Either way, multiplication doesn't matter. In Cal 1, we learned that if you take the derivative of a product, right, we have to do the product rule, right? That little mark means derivative. So it would be, what, u prime v plus v prime u. And I think we already discussed how different people learned it different ways, but it's all the same, right? Everyone agrees with this? That's the product rule from Cal 1. This new formula, integration by parts, builds off of this, actually uses this to figure something out. So look at what I'm going to do. I'm going to take this product rule. We got it from taking the derivative. I'm going to come in on both sides of the equation right now, and I'm going to undo the derivative. So if I undo the derivative, what I mean is find the antiderivative. So what is the antiderivative of u times v, like this? And then over here, the antiderivative of this, and then plus the antiderivative of this. So do you see what I've done is I've taken the product rule and I've taken the antiderivative of both sides. On the right side, I can do antiderivative of each one because it was a plus. I can do that, right? Understand? All right, so this right here is an eraser, right? If I say, hey, take the derivative of this eraser and then undo that, what am I going to be left with? The eraser, right? So it's like take the derivative and then take the antiderivative, then it just comes out unchanged, doesn't it? So the left side of this equation becomes u times v. Agreed? Yeah? Okay, u times v. So the left side is u times v equals, now the right side, I actually cannot tell you what the antiderivatives of these are because these are products, right? I can't split these apart. I'm not allowed to do that. So these, I don't know. I actually have no idea what those are. But I know that when you add the two together, you get this. Understand? Now, how is this going to be used? What I'm going to do is I'm going to take this one right here, okay? This one right here. And I'm going to subtract that integral from both sides of this equation. I mean, it's an equation, so I can move things around with addition and subtraction. I'm going to take this, leave it here, bring this over to the other side so it looks like this. uv minus integral of u prime v plus, not plus, it's equals now, equals this. Understand? Just manipulating things algebraically. Now I'm going to do one more thing. Let's see if you can follow me on this. Because this is an equation, it doesn't matter which way I write it, right? Like if I put, x equals 4, I could put 4 equals x. It's the same thing. So I'm just going to switch the order. I'm going to put this integral on the left. And I'm also going to write the u in front of the v. And instead of writing v prime, I'm going to use a different notation. I'm going to use Leibniz notation. I'm going to write dv here to represent the derivative of v. Right, so does everyone see that's this? Equals, now the other side is this, right? So I'm going to write uv minus integral, and then here I'm going to rewrite this as v times the derivative of u, so I'm going to write du. Does anyone have a question on where this came from? Started with the product rule, integrated both sides, then everything was just algebra after that. And that's it. That's the integration by parts formula. But you look at it and you're like, so what? Like what does this do? Are you raising your hand?
Yeah.
Yes.
I just have a question. When you moved over the v integral v prime u, wouldn't it be negative?
Yeah, it was. It's right here.
Oh, okay.
Yep.
Oh, okay.
Right. I moved it over so it became minus.
Oh, okay.
And then when I changed the order of these, I didn't switch sides. I just rewrote it. Okay. Equality doesn't matter which way you write it.
I see what you mean.
Okay? All right. This is so fundamental. I can still remember Dr. Richardson trying to just drill this into my head when I was a student in this class. And he went on to teach me a lot of things in mathematics that now that I look back at this, it's like this is the one thing I want students to take from this formula. And if I can get it across like he did, then it's a good thing. So hopefully this will work. All right, we start with an integral, right? Within this integral, we have u, which we said was a function of x, right? So you just have some function of x sitting here. And then next to it, you don't have a function. I mean, it's a function of x, but it's actually the derivative of something, right? So this would be the derivative of some function. I'm going to call it g. So you've got this integral. You've got some function of x times some other function, but it actually is the derivative of something. Sitting together in an integral, and you're sitting there and you're scratching your head and you're going, I have no idea how to do this, right? Well, it turns out, according to this formula, that what you need to do to figure out this answer is just do the u times the v, which would mean this function, f, right? F of x. What would v be? It would be the antiderivative of g, right? Because if dv is g prime, then g would be v. So this would be g of x. Understand? Minus a new integral. Now this new integral is what? What's v? It's g of x. And then what's du? It's the derivative of which function? F of x. Okay, so let's really try and focus on what the hell this is allowing us to do. We start with something, we're scratching our heads, we have no idea how to do it. This formula allows us to transform this derivative, this integral, into a new integral with some junk in front, right? But this new integral is different than the original one. In which way? How is it different? Instead of, yeah, it's backwards. Instead of f here, what am I going to have over here? Its derivative. And instead of the derivative of g, what do I have over here? Its antiderivative. And the hope is that this integral is easier than this integral. What we've done, though, is we've transferred the derivative. Here, f did not have a derivative. In the new integral, it does. Here, the g does have the derivative, or is the derivative of g. Here, it is not the derivative. So you see the derivative switch places, and that's what I can remember Dr. Richardson saying, is that the integration by parts, IBP is what I call it up in the notes, is transferring of the derivative. That is the beauty of the formula. You transfer the derivative over from one function to the other. Now, a way to remember this formula, because it's hard at first to remember it, is a little saying. Where is it? There it is. Ultraviolet minus voodoo. It's one of these things that once you hear that the first couple of times, you'll never forget it. Ultraviolet minus voodoo. So it comes from this. Ultraviolet minus voodoo, right? Voodoo. You have to remember the integral sign, okay? But if you kind of get that hardwired, I've remembered that ever since I was told the first time, right? So you use ultraviolet minus voodoo. I have just 5 minutes. I want to show you one example of integration by parts. And we're going to do a simple example. And this is a good example because you can't do this any other way than integration by parts. There's no other way to do it. Well, you can do it numerically with chapter 8 later on, but we're not there yet. All right, so let's run through a couple of things here. You can't use the power rule, right? You can't split this into two integrals, right? Because it's a product. So you can't say, oh yeah, the antiderivative of x is 1/2 x squared and the antiderivative of sine is negative cosine. We talked about that last class. That Cal 2 would be too easy if that's the way it was. So we're trying to undo the product. How about a basic substitution, which is what most of today was about? Do you see something and its derivative? I see x and then its derivative is 1, but we said don't you do that. What are your only other choices, really? Sine x as your u? Do you see its derivative there? Cosine x? So you can attack this with basic substitution all day long. Nothing's going to happen. Instead, though, let's try and attack it with integration by parts. So the thing about integration by parts is you have to make a choice. You have to look at your function, your integrand and everything here, and you have to make a choice. What is going to be your u and what is going to be your v prime? Right? The formula looks like this. Integral uv prime equals uv ultraviolet minus v du, which is that, right? So something there has got to be your u, and something else has to be your v prime. So let's look at our options. What's one thing I could choose for u here?
X.
I could choose yet x to be our u, right? So I'm going to make a list of possibilities. I could let u be my x. In that case, what would my v prime be? And what would my dv have to be if I choose my u to be x? I think I like this formula written a little different. Hold on, let me do it this way. dv du, okay? That's a v. Okay, if you come in here and you say that's going to be my u, what's the dv? What's not?
Cosine u.
No. It's everything else that's there. You don't do any derivatives or anything. See, we're going to say one of these, this piece right here is the u, right? that means everything else has to be the dv. So dv would have to be the sine x and the dx. Understand? That's one thing I could do. What's another possibility I could have used? Or I could have chosen for my u the what? The sine x, which would then force me to use x dx, the only things that are left, as my dv. Can anybody tell me which one of these? Well, is there another possibility? I mean, I chose this for u once, and I chose that u for once. You don't ever choose dx to be your u. Okay, that you just never do. So, which one of these should I use? What did I tell you integration by parts is? It's a, that's right, the new integral, right? But we are going to transfer the derivative, right? Transfer the derivative. So what we know is that if I do it this way, in my new integral, I'm foreseeing, I'm looking into the future. In my new integral, instead of working with u, I'm going to be working with what? The derivative of it. What's the derivative of x? 1. And then here, instead of working with dv, my new integral will have what in it? The antiderivative of this, which would be negative cosine x. So my new integral is going to have a 1 and a cosine in it, which is just cosine. Isn't that a nice integral? Versus this one. Now, if I do this, what is my u going to turn into in the new integral? Cosine x, that's fine. But here, dv is going to become v, and that means I need the antiderivative of this. And what's the antiderivative of this going to be in the new integral? 1/2 x squared. So what would you rather have? Would you rather have a 1 and a cosine, negative cosine, or would you rather have a cosine and a 1/2 x squared? The first one, right? So this one is a poor choice, and actually integration by parts won't work if you choose that one. Understand? Do you kind of see this? I have to finish it. I'm out of time though. So should I just leave that as an open thing, or should I finish it? You want to finish it? Okay. So different instructors have different ways of doing this. This is the way I do it. If you don't like it, find your own way. I always just make a table, and I always write down u here and dv here. These are the things I will have to identify every time I do integration by parts. I have to identify what my u is, what my dv is. U for us, we said the best choice was x. In dv, we were forced to use sine x dx, right? Yes? All right, now from here, the reason I wrote this table like this is because in my new formula, I'm going to need the opposite of these. So in my new formula, I need the derivative of u, which would be the derivative of x, which is 1 dx. Don't forget the dx. Right? 1 dx. And then here, in my table, I have to go up in the table, which means antiderivative. What's the antiderivative of v? Antiderivative of v is going to be v. Negative cosine x, right? No dx. So do y'all see that the step from here is actually an integral? You have to do the integral of this and go up to here. And now we plug in the formula. This, according to my formula, this will turn into ultraviolet minus voodoo. So what's ultraviolet? U and V, right? Ultraviolet. Multiply those two together. What is it? X times this, negative x cosine x, minus integral voodoo. And voodoo is going to be this diagonal right here. Voodoo is this times this. So negative cosine x dx. The minus can come out and become a plus, right? So I have negative x cosine x plus integral cosine x dx. And now it's time to find the antiderivative of cosine, which is an easy one to do, right? It's just sine. So our answer is negative x, cosine x, then what? Plus sine x, and then plus Christie, right?
Yes.
All right. Plus Christie. That's it. That's the antiderivative. We will definitely have to do a lot of examples of this. And I don't want to give you any homework from this because I want you to focus on substitution. You're free to pack up and go. While you're doing that, I'm going to take the derivative of this to prove that it is correct. So I'm going to do product rule here. Derivative of this is -1 times cosine x. Product rule plus derivative cosine, which is negative sine x, times the first one, which is negative x, and then plus, now derivative of sine x is cosine x. And so when I put these together, it should work. These cosines cancel, and then this is a negative x, and then here's a negative, I bring it in front, that's positive x sine x. And that was the integrand. Okay. Have a good weekend. We meet again on Tuesday, right? So we don't get that holiday. Monday is a holiday, though. All right.